right, why don't we get started? It is a minute past the hour at this point. So hello everyone, thanks for joining today's webinar where we will be talking about pets, privacy enhancing technologies, and privacy lab at the Tech Lab. I'm Rowena. I'm the Senior Director of Privacy and Data at the Tech Lab. So I steward all of our initiatives related to privacy and addressability. And I'm really excited to have Lucio, who is a digital advertising product manager at IAB Europe, joining me today to talk about the work that IAB Europe is doing around pets as well. So welcome, Lucio.
Thanks. Hi, everyone.
And so just for those of you who are joining today who perhaps are not as familiar with Tech Lab, we're a member-driven organization. We have more than 1,000 organizations that participate in a variety of working groups. And what our mission is to develop global, open, interoperable technology standards that support the growth of the secure and private ad-supported digital economy. We steward many specifications, and not just ones that are related to privacy. Some of the ones that you may be intimately familiar with are OpenRTB, sellers.json, OMSDK, our AMP initiative. I'm sure many of you have heard of. So lots of different specifications. And in the world of privacy, things like the technical specifications for TCF, GPP, Global Privacy Protocol, etc. And so today, as I mentioned, we're going to be talking about pets. And a little bit of a spoiler alert. If you are not familiar with what the Privacy Lab is and what's included in the Privacy Lab, it is a playground where you can start interacting with a handful of specific pets. Before I actually do a demo of the Privacy Lab, I'm going to walk through 3 different pets: anonymity, differential privacy, and homomorphic encryption. And those are the 3 that you can actually today engage with in the Privacy Lab. So following just quick, I would say, introduction to each of these, we'll do a demo of the Privacy Lab. And then Lucio and I are going to go into conversation about the specific work that IAB Europe is doing around pets in their pets working group. And of course, we'll have time at the end for audience questions. And so you should have a function where you can pose your questions, and we'll make sure that we answer them towards the end. So I'm going to start with k-anonymity. And so what this is, it's a method where data is aggregated to a minimum privacy threshold, ensuring that at least a minimum number of data points with identifiers removed, known as K, are included in the results. And 2 of the techniques to use to achieve k-anonymity are generalization and suppression. And so, again, this will ensure that at least a minimum number of data points with identifiers removed are included in the results. And I always find that it's helpful, to actually walk through an example to better understand these pets. And so I'm going to do kind of an academic example. This is obviously not necessarily specific to our industry, but in this example, let's say that you're trying to understand the average salary of a group of people. And so on the left here, this is the original data set that you have, and you want to allow for some intelligence to be gained on the data without actually providing access to the raw data set, which, as you can see, is grouped to unique users. And so on the right, what you see is this is a combination of both generalization and the suppression. We are k-anonymizing the data set with a level of what we're calling k equals 2. And what that essentially means is that there are now at least 2 rows that are indistinguishable from each other. And you can see, for example, where we've applied suppression from the data set is in the name. So you can't see the names anymore. And the other thing you can see is that age is generalized into buckets. And then the last thing that we've done is that the last digit in each of the individual rows zip code is also suppressed. And so now that we've applied both suppression and generalization, this data set has now been transformed so that rows 1 and 2, for example, are indistinguishable from each other than the salaries. And the same thing is the case for rows 3 and 4. From here, even though we've applied that transformation, you can still learn things from this data set, but without the ability to isolate any individual, right? So you can still do things like calculate the average salary, which is the primary goal of this example. But you can, calculate the overall average salary, but you can also learn, for example, the average salary for those who are in the, for example, 40 to 50 age bucket or the 20 to 30 age bucket. So that's just a very quick example of pay anonymity. And the next one that I'll go through briefly is differential privacy. And so with differential privacy, what you're essentially doing is adding noise to reduce the risk that any individual person can be identified. And differential privacy is essentially math. And what it does is it allows you to calculate how unlikely it is that identifying information can be released, and ultimately how difficult it would be to reverse engineer identifying data. Again, I find it helpful to walk through specific examples to understand exactly how this works. So in this example, let's say that a publisher is looking to understand the number of conversions from an attribution service. And let's say that the attribution service doesn't actually provide you with a list of conversions, but it will give you an aggregate result if you ask for it. And so in the table in the middle with email address and conversions, that's the information that an attribution service has on conversions. And this is not revealed to the publisher, right? So as a publisher, if I execute a query that asks if Alice, so the one on the left, this is query 1, I'm asking if Alice, Carla, Gina, and Henry contributed to any conversions. The attribution service returns query result 1 that you see on the right, and it says that group you sent to me, so Alice, Carla, Gina, Henry, contributed 3 conversions. Now, if a publisher then runs the second query that only includes Carla, Gina, and Henry, and asks that same question of how many conversions did this group of individuals contribute, they're going to get a result back from the attribution service that you see in query result number 2 of 2 conversions. So just by omitting Alice in the second query, the publisher has now learned that Alice has actually contributed 1 conversion. With differential privacy, there is noise added. So using the same example, when the publisher asks the attribution service who is actually applying differential privacy before they provide the publisher with the answer, you won't learn anything new. In the middle table, those are the actual conversions that the attribution service has recorded. And in the table to the right, those are the conversions with differential privacy applied. And in this particular example, they're returning a 1, meaning this person converted, with a 60% probability, and a 0 with a 40% probability for each matched conversion. So for Carla, in this case, even though she actually did contribute a conversion event, in the results shared back to the publisher, her matching conversion event was treated as a 0. And so therefore, the result given back to the publisher was 2. The last one that I'm going to talk through a little bit is homomorphic encryption. So what this is a method of encryption where computations are performed directly on encrypted data without decryption, and it allows or ensures sensitive data is never exposed during the processing. And 2 of the common operations that are supported are addition and multiplication. Now I'm going to be upfront and say that this example is probably a little bizarre because I find that trying to showcase homomorphic encryption in an example is the most challenging one. I totally acknowledge that this is probably not a real use case. Why would someone actually leverage homomorphic encryption for something so simple? But hopefully it still helps nonetheless. So in this example, I have two entities. There's an advertiser and we'll say a cloud provider. And let's say that the advertiser wants their cloud provider to process certain information about campaigns that they're running. In this case, in this example, they want to understand total ad spend. And so the advertiser, what they would do is they would use homomorphic encryption to encrypt this raw data set before they actually give it to the cloud provider. And then what the cloud provider is going to do is they're going to be able to actually do the computation on the encrypted data. And the result of the computation also is encrypted. It remains encrypted. And that encrypted result is what is then provided back to the advertiser. And the advertiser would have the appropriate keys to actually decrypt that result. And so in this case, leveraging homomorphic encryption, the cloud provider never sees the raw data. They don't see the result either, even though they've performed the computation. And only the advertiser ultimately is able to see the raw result.